This is Free Range Digital Design Foundation Modeling, Chapter 10. This chapter we are going to add all the final gates in digital design, which is the NAND, NOR, XOR, and XNOR gates. And along with those gates comes some useful functionality that we'll be talking about. And finally, we'll discuss functional completeness. So the NAND and NOR gates typically stand for not and not or, so that's where not and, NAND, that's where that comes from. It's modeled as a gate, typically like an AND gate with an inverter on it, which is not exactly what it is, but it's often modeled that way. So, and the NOR gate is very similar. It looks like an OR gate with a inverter on the output, modeled that way, not really that way. Both these gates have distinctive symbols, which is this is the NAND, this is going to be the NOR, so that inverter is essentially modeled with a bubble on the output. People, once again, think these are typical AND and OR gates with inverters, but there's a little bit more to it, which we'll get to in chapter 14. Also, the best way to model these things is possibly with a truth table, so we'll do that. This is a AND gate definition we've been working with, and essentially this means the output is a 1 when all the inputs are 1. And so if I invert that, it's going to be 1 1 1 0. That is my output for a NAND gate. Now we do the same thing with a NOR gate. A, B is your standard OR, which is 0 1 1 1. OR gate, the output is 0 if all the inputs are 0. Otherwise, the output's 1. Okay, there's your NOR. A plus B is the opposite of this OR column, which is 1 0 0 0. So these are the definitions and the distinctive symbols for NAND and NOR gates. The XOR and XNOR gates are a little bit different than the other gates. They have distinctive symbols, but they're best defined using a truth table. First, we'll do the symbols. So this is an XOR. It looks kind of like an OR gate, but it has that little extra back end on this, as you could probably guess. An XNOR gate is going to be the same thing with a bubble on the output. So let's define these with truth tables. Okay, first of all, the circled plus is the operator associated with XOR, and the definition is 0 1 1 0. This essentially means the output's a 1 when one and only of the inputs is a 1. Output, this is XNOR, this is XOR. The output is going to be the opposite of the XOR, so it's 1 0 0 1, and that's it. Typically, this gate here is also known as an equivalence. Known as an equivalency gate because the output is a 1 right here and right here when the two inputs are the same. And this typically has a distinctive symbol. You can put an overbar over an exclusive OR and make an exclusive NOR, or sometimes you see it written like this, which is a circled dot. This symbol, you don't see it too often because many of the typical drawing editors out there don't have it. These gates are a little bit different from the NAND and NOR and 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 OR in that these are only defined for 2 inputs and 1 output. You can't have a 3 input or a 4 input XOR or an XNOR gate. The AND gates and NAND gates, the OR gates and NOR gates, they're all defined for 2 or more inputs, and we've gone over that definition before. This is XOR and XNOR is only defined for 2 inputs and 1 output only. Now the NAND and NOR gates can be easily configured to act as inverters, and let's show that. It's easy to show with a table. NAND gate 1 1, 1, 0. So there's two configurations to configure a NAND gate as an inverter. The first configuration is to short the inputs together. Now when I short the inputs together, I'm essentially looking at these two rows right here. So in these two cases, the inputs are the same, but the output is different. So that is one inverter, one way to model an inverter. The other way is to, let's change the colors here, is to notice, essentially it's to tie one of the inputs high. So if I tie one of the inputs high, tie it to the power rail, you'll see that the output here is the opposite of the other input. So the output's a 0, the input's a 1, output's a 1, input's a 0. So once again, this is another way to do an inverter, which is going to look like this. There's my tied high. Now I went through this kind of a long way. I'm just going to plop it out there, the two ways to make a NOR gate into inverter. There's one, and here is the other one. In this case, I am tying one of the inputs to 0, tying it to ground. Once I do that, it becomes an inverter. These are your NOR inverters, and these are your NAND inverters. You use that quite often. It comes up quite often. The same functionality exists for an XOR gate, a little bit different. There's only one way to do it, but let's look at this thing. The issue here, I'm just going to plop it out there. There's the XOR gate. If I tie one of these inputs to 1, essentially what I'm doing is these two columns right here. In this case, one input's tied to 1. If the other input's a 0, the output's a 1. Otherwise, other input's a 1, output's a 0. This is my inversion function. You can do a similar thing with an XNOR gate. I'm not going to do it here. Left as an exercise for the reader. Now the AND gate has some special functionality. We've seen this before in an example problem in a previous chapter. Now there's two things you can do to an AND gate here. One, or a couple of things. If you tie input to 1, the output is not going to change. The tie an input to a 1, the output is going to be the same as the other input. Conversely, if I tie input to 0, which I ground it, the output's always going to be 0. So it doesn't matter, in this case, it doesn't matter what the other input is. Anytime I have an AND gate with a 0 tied to it, the output's always going to be 0. Now this is a little bit different. This is essentially, when I configure a gate like this, it allows the data to pass through. When I configure a gate like this, it essentially kills the data. The output's always a 0. So let's use that functionality in a problem here. And here's our problem. What we have is an example problem design circuit that adds two 4-bit values. If the addition operation generates a carryout, the 4-bit sum is all zeros. Otherwise, the 4-bit output shows the sum of the two 4-bit inputs. Okay, and we want to state what controls the circuit. So this is a simple, fairly simple circuit. We'll call it circuit. It has two 4-bit inputs, and it has a 4-bit output, sum for lack of a better word. Okay, so the notion here is the sum is going to be all zeros if the addition of this a plus b generates a carryout. And so I want to take advantage of the fact that tie the output, send it through these AND gates like we did in the previous slide. So that means when the carryout is a 0, that's where I want to show the answer. So what I'm going to do is invert that carryout and feed it into an AND gate for each of the outputs, for each of the single bit outputs. Otherwise, if there is a carryout, it's going to be inverted, it's going to send a 0 to those same AND gates, and it's going to kill them. And so let's go ahead and draw that. It has an internal RCA, feeds those 4-bit inputs into this thing, this A and B. And so what we're going to do here is have this 4-bit sum, but we're going to break it up into 4 AND gates, and we can reconstruct it here. This is going to be MSB. This is the LSB. So what I'm going to do here is invert this carryout and put that into each of these AND gates here. So what happens here, when there's no carryout, this is a 0, it becomes a 1 by the inverter. The 1 is feeding into those AND gates. It lets these individual bits feed through those AND gates to the output, gets reconstructed in the output. So if there is a carryout, the carryout becomes a 1, it gets inverted to a 0. The 0 essentially kills those AND gates. And there is my circuit. This circuit is essentially, it has a little bit of control in there. It has essentially, it's done by this internal circuitry. So this is going to be internal control. So what you're going to see in a later chapter is this functionality here is much easier done with another circuit, and we'll happily go over that in another chapter. But this is typically a use of the AND gate that's like to know about. It essentially allows you to either pass an input signal through it or pass a 0 through the gate.